guys. First of all, welcome to our first colloquium talk. First of all, I really kind of apologize. There is a error at the link, at the flyer for the link. So today we have Dr. Jaffer Zaidi from CMC. Dr. Zaidi is the CMC Causal Inference program, is at the Causal Inference program, and is a postdoctoral research associate at the University of North Carolina at Chapel Hill, mentored by Professor Michael Hudgens. And he received his PhD in biostatistics from Harvard in 2019 under the supervision of Professor Tyler Vandervelde. His dissertation research concerned causal inference, and he has established empirical conditions to detect and quantify individual level causal interactive effects, direct effects, and always survival causal effects under randomization at baseline. He's also beginning to investigate causal effects under contagion and interferences. His research application areas include, but not limited to, drug resistance, parallel epidemiology, and clinical trials. So today is really, we are very happy to have Dr. Zaidi here to give us a talk. And yeah, it's your.
Thank you. Thank you for the very kind introduction. I'm very happy to present at the colloquium. This is my third dissertation paper. So the joint work with Tyler and Eric Chekin. Originally, at the end of my PhD, I wrote one version of this paper. And we got reviewers' comments, and it ended up being that we had to completely rewrite the entire paper. But it was for the best. One thing I'd like to say is, in some sense, this topic actually concerns all of us. You know, when the FDA decides to go forward with a new treatment, you know, they run a clinical trial, right? So especially in the case of, you know, COVID, with these new vaccine trials, we really need to have sound methods to assess whether the new treatment is better than the old treatment. But there are many issues that occur. So we'll just very quickly consider, you know, what would be the ideal situation in a clinical trial. So in the ideal situation, you know, you have a large one. People are just randomized to a new treatment and old, so just a binary treatment. And then after some time, you get to see whether, you know, individuals are cured or not, right? So just notation, you just have a binary treatment X, a binary outcome Y, and then name and introduce this idea of a potential outcome, right, or potential yield. So had I given you treatment, so your Y1, what is your outcome? Had I given you the control, what is your outcome? So you can consider this for all of us, right? So for each individual in the population, you consider what would have happened under the treatment and under the control condition. And then you finally name and, you know, establish that you could consider this counterfactual distribution, right? So you can consider this set of individuals, say like my brother, who regardless of treatment would have been, you know, if Y1 is, you know, whether they're alive or not, they would have been alive regardless of, you know, whether they got the new treatment or the old treatment. Now you can consider the unfortunate people like me that had you given them the old treatment, they would have lived, but had you give them the new treatment, they would die, right, at the end of the trial. And then finally, you can consider the set of individuals like yourself who, when you give them the new treatment, they live, but with the old treatment, they die. So these individuals benefit from treatment. And finally, the last set of individuals are, you know, maybe perhaps like a cousin of mine that regardless of which treatment you give them, they would die. So these are the 4 states of people that you can imagine in your clinical trial. Ideally, you know, and the decision is for all of us, right? So we would ideally want to know for each one of us, what is the best treatment to take? But once you give an individual one treatment, you can't know the other counterfactual. So that's the fundamental problem of causality, is that once you have given one treatment, you won't know what would have happened otherwise. But what we do is we randomize to learn something very useful. So the idea then is by randomizing, you can actually get very useful information about the, the proportion of individuals that benefit from treatment minus the proportion of individuals that are harmed by treatment. And this is very simple, so you begin with imagining for each individual in your population, just what would happen, had you given them the treatment condition and the control condition, then it's just linearity of expectations. The expectation of a binary outcome is just just the probability of success. So there's nothing big going on in these first three lines. And then finally, with the randomization assumption, you can just subset on the people who actually receive treatment. So this proportion here, right, will be equal to this proportion here, because the treatment assignment is just decided by the toss of a coin. So it doesn't matter had you randomized 100 people at the beginning to all 100 people got the new treatment, or you had just given those 50 people that you randomized. And the same for the control condition. And then finally, you apply this consistency assumption to get to what you actually get to see in the data. The proportion of individuals that are cured in the treatment arm minus the proportion of people who are cured in the control arm. So this is quite useful. And then finally, we want to relate this quantity, right, to something that is clinically meaningful to the doctor, right? So you want to really talk about joint potential outcomes. So this quantity is equal to the proportion of individuals that benefit from treatment minus the proportion of individuals that are harmed by treatment. And you get this very quickly by two methods. One, you can just apply the law of total probability at this line, expanding over the other counterfactual variables. Or you could just take the expectation at the beginning of this probability table. So it's very straightforward. Now, what's the issue? Even in the most simplest setting, if the individual has died before you get to see the outcome of interest, say it's like, cancer progression, quality of life, and more people have died in the treatment arm, or say in the control arm in comparison to the treatment arm, then it's difficult. So that individual level counterfactual contrast doesn't make sense. Say if I'm still alive and I have a good quality of life under the treatment arm, but I'm dead under the control condition, then this individual level counterfactual contrast isn't defined even. So we have an issue of, in mathematical terms, this doesn't even make sense. On the population level, we've known this for a very long time. So, many very senior statisticians have worked on this problem, right? So, the fine and gray model for this issue is a very popular model. Frangakis and Rubin have talked about this problem. Zhang and Rubin have talked, Jamie has talked about this problem, and a lot of statisticians have, talked about this problem. What Rubin and Frangakis proposed to overcome this problem was, say if we could condition on the set of individuals that regardless of treatment would have made it to the end of the trial, and then you calculate the average treatment effect. So we draw inspiration from this approach, but that's not exactly what we're doing. We do something similar. So instead of calculating what they're proposing, we say, can you calculate the proportion of individuals regardless of treatment would still be alive at the end of the clinical trial, and then treatment causes the outcome of interest, minus the proportion of individuals who regardless of treatment would still be alive, but treatment prevents the outcome of interest. We do this for a couple of reasons, but the chief one amongst them is the identification assumptions we use is only randomization at baseline, which is guaranteed by the design of the clinical trial. So it's really nice that all the interpretations of our results are concrete at the individual level and are guaranteed by design of the clinical trial. So we apply our results to this clinical trial to illustrate why it's a good thing to do. So let us, for the sake of concreteness, and to reinforce that really we want to implement, the most judicious and most justified use of our data, right? We want to implement methods that are really justified. Let us imagine this is our data. So there's 336 of us on this doxytaxel arm. There's 336 of us on this metotaxtrone arm. In 4 years, unfortunately, all of us are dead. But the study investigators suggest that, that doxytaxel improves median survival in comparison to metotaxtrone. Now, the gain in life is modest. At most, it's like around 3 years, but it's there. And the other thing the study investigators look at was, does doxytaxel delay cancer progression in comparison to metotaxtrone? And the answer that they suggest is also yes, that doxytaxel delays cancer progression. So we further disentangle this relationship, and we also look at quality of life. Is the quality of life actually better on doxytaxel in comparison to metotaxtrone? So the data is very simple, right? Binary treatment doxytaxel versus metotaxtrone. We have data on survival. People can drop out, and they might well drop out more on the metotaxtrone arm in comparison to the doxytaxel arm, which might make inferences difficult. So here it's just very simple notation. For all of us, you can consider if they're alive at, say, 1 month, t is equal to 1 month, then their s is equal to 1. If they're dead at 1 month, then their s is equal to 0. And then the next thing is just the cancer progression status, right, at each time in the clinical trial. So if they've died and they're cremated, say, at 1 month, then you really should just say that they're dead. You really can't talk about their cancer progression status. If they're still alive at 1 month and their cancer has progressed, then you just say their y is equal to 1, right? And if they're alive and their cancer has not progressed at 1 month, then you just say that y is equal to 0. So we've defined the factual variables, and we just define one more variable related to almost like a missing data indicator, right? So if either y or s is not missing, you just say r is equal to 1 at each time in the clinical trial. And if either one is missing, then the r is equal to 0. So we've defined the factual variables, and in the same way, you would just define the counterfactual variables or the potential outcomes. So for all of us, say for Jaffer, you would imagine, my cancer progression status at each time post-randomization, my survival status each time post-randomization, and whether I've dropped out, of the clinical trial each time post-randomization. And you would do it for the treatment and for the control conditions. So this is just very similar notation. So in the interest of time, I will skip the notation for the potential outcomes because it's very similar to the factuals. And then I'll just say the 2 assumptions we need, right? The only assumption we need is really randomization at baseline. So at the toss of a coin, if the coin clip comes out for me as heads, I see my my y1, my s1, and my missing data indicator, right? My r1. So my cancer progression status under treatment, my survival status under treatment, and my response indicator type under treatment. Now for you, if it comes out tails, you see your y0, s0, and r0. So it's just a very simple assumption. And the other assumption we need is just this idea of a consistency assumption, which is violated in the case of infectious diseases, right? So if one person's outcome influences another person's outcome, then this assumption doesn't hold. Or if one person's treatment decides someone else's treatment, then this assumption is violated. But in our setting, it's not, we know that, one person's cancer doesn't influence another person's cancer. Cancer is not infectious, and treatment is decided by a toss of a coin. So it's not going to be the case that this assumption is violated. Even if it is, it's not going to drastically, give us erroneous results. But for our situation, we're fine. So with these 2 assumptions, we hit the individual level identification result. And all I'm saying is, at any time, so say at 1 month post-randomization, go to the treatment arm, calculate the proportion of individuals who are still in the trial at 1 month, still alive, and whose cancer has not progressed. Then add to that in the proportion of individuals in the control arm who are still in the trial, who are still alive, and whose cancer has progressed. And if the sum of these 2 probabilities is greater than 1, then you know that there's a set of individuals in your population, a non-MC set of individuals in your population, that regardless of treatment would still be alive at 1 month would still be in the clinical trial at 1 month, but whose cancer would progress with the old condition, metotaxone, but not docetaxel. And the next question you will ask is, well, which individuals? If we could know exactly which are the individuals, then we would just treat those individuals, right, with the new treatment and not treat the other ones, potentially. But the problem is we will never know exactly which. Under some situations, you might get very close, but still it'll be, somewhat speculative. But the next best thing we can do is actually talk about how many individuals are that response type, right? So taking this one over to the other side, we have that this expression is a lower bound on the risk difference between the proportion of individuals that, regardless of treatment, are still alive, and whose cancer progresses with the old treatment, metotaxone, but not docetaxel, minus the proportion of individuals, regardless of treatment, are still alive, but whose cancer would progress under docetaxel, but not metotaxone. So it's nice, and we'll see how you could use this identification very nicely in the actual data analysis in a moment. Now, reviewers asked me, can you do the same thing with continuous outcomes? And the answer is yes, and we'll see that in a data application in a moment. Now, this empirical condition actually can be a little bit stringent, but in very bad statistical jargon, it actually is the least favorable configuration, actually. So you can if this is less than or equal to 0, you can always construct counterfactual distributions where there's no individual in your population that is an always survivor, would never drop out, and their cancer progresses with metotaxone but not docetaxel. So in a way, this bound is the sharpest bound you can imagine. You can't really do better than this with randomization alone. So as a clinical trial goes on, though, you might want to do better. And the two assumptions you might consider are monotonicity assumptions. So the previous assumptions, just use randomization alone, which is guaranteed by the design of the clinical trial. But two assumptions that we really should consider. Hello, are people still there?
Yeah.
Yeah, you're still there. Okay, sorry, I apologize for that.
Well, fine.
So, the two monotonicity assumptions are survival one. So the first one is that, you don't expect individuals to die under the new treatment in comparison to the old treatment. So there's no individual like that. And then the second one is that you hope that the new treatment is less toxic in comparison to the old treatment. So Jaffer wouldn't drop out if you gave me the new treatment, but I would remain in the trial if you gave me the old treatment. So that sort of individual is not allowed. Now, the immediate question I get is, well, these assumptions look too strong. They're at the individual level. And you could never really know that these assumptions hold. You can falsify them, so you can know when you're not in that situation. Additionally, we can do very good sensitivity analysis for these assumptions, which I'll describe. But first, why you would posit these monotonicity assumptions is you end up with a weaker null condition. So to detect, these sort of individual level effects, right? An always survivor, who doesn't drop out, whose cancer progresses with the old condition, metotaxone, but not docetaxel, is given by this null probability with randomization alone, right? And the moment you make the monotonicity assumption on survival, you can drop the probability associated with in death in the treatment arm. So you end up with a weaker null hypothesis. The moment you make the monotonicity assumption on missing data, you can drop the probability associated with missing data. So you end up again with a weaker null hypothesis. And when you make both monotonicity assumptions, the survival and the missing data, you end up with just a simple risk difference, which is very easy to falsify, to reject potentially. So we apply our results to this clinical trial. I'll just get very quickly into the sensitivity analysis. It's actually really nice sensitivity analysis, very interpretable sensitivity analysis. So with randomization alone, you need no sensitivity analysis, right? But if you make the survival monotonicity assumption, this is the expression that's less than or equal to 0 forms your null hypothesis, right? And there's this bias term DMT. So this expression minus DMT is equal to the counterfactual contrast that we're interested in. And this DMT is a causal bias term. So it's a risk difference of counterfactual proportions. If it is positive, then we're overestimating potentially, the thing we're interested in. So that the bias is going in the wrong direction. If the bias is negative, then actually we're okay. And so the only positive term in this thing is this expression here. And it's once you've established that treatment is actually effective in extending life, then this will very likely be very close to 0. So you can do very nice sensitivity analysis in this situation. So if you calculate, this expression here to be, a quarter, what you're really saying is that, and at most you expect 10% of your population to be of the wrong response type. So they would have lived out you given the old treatment condition, but died if you give them the new treatment, docetaxel. Then the counterfactual contrast you're interested in is at least 15%, right? And further, you can refine this by looking at exactly what DMT is, right? So in the situation where, the new treatment is actually going to extend your life, and you see this by the Kaplan-Meier curves, it's very likely that DMT is actually negative. So you're actually underestimating the causal contrast you're interested in. And we'll see this in the data analysis. So I'll get straight to the data analysis. There's another sensitivity analysis that if we have time, I can show you how that's used in a data application. So I'll come straight to our data. This is our data, right? So there's 336 of us on the docetaxel arm, 338 of us on the docetaxel arm, 336 on the metotaxtron arm. 6 of us are still alive. Our cancer has progressed, and we're still in the trial, right? So at each time point, we see what's happening to our cancer progression. And then those of us on the metotaxtron at 1 month, 2 months, 3 months, we see exactly what's happening to us as well. We see what's happening to us in terms of dropout, right? So 9 of us had dropped out in the docetaxel arm. 15 of us have dropped out at 4 months in the metotaxtron arm. And then we look at, finally those of us that we see dead, right, at each time point. So 14 of us have died at 3 months in the docetaxel arm. 25 of us have died at 4 months in the metotaxtron arm. So this is really the only data I need to draw causal conclusions. I don't need baseline covariates, which is quite nice. So as I mentioned earlier, this is our null hypothesis to detect individuals, regardless of treatment, will still be alive, but their cancer progresses with metotaxtron, but not docetaxel, right? So these are the type of individuals we want to tell our investigator exist in our population. So you really want to be giving docetaxel in order to delay cancer progression. And so that's what we do. We seek to reject that null hypothesis, right? So this null hypothesis is equivalent to this null hypothesis. And this is just a one-sided difference of proportions. So you can just apply the standard t-test to reject this null hypothesis. And that's what we do. So we see the estimates of the factual contrast we're interested in. We see it at 1 month, 2 months, 3 months, etc. We provide the one-sided, p-value, the associated 95 and 99 two-sided confidence intervals. And we do the same thing for 4 months, 6 months, 12 months, right? So when you first look at, these estimates, they're not very interpretable in terms of just the factuals, right? But they become very interpretable when you, take it back to the counterfactual interpretation, right? So this 0.07 at 1 month is very nice. What it's saying is that, there's statistical evidence that regardless of treatment, the proportion of individuals randomized at baseline that are always survivors at 1 month post-randomization, whose cancer would not progress under docetaxel, but would progress under metotaxtron. So this thing here, the proportion of individuals of this response type, is 0.07 more than the proportion of individuals randomized at baseline that are always survivors at 1 month post-treatment, post-randomization, whose cancer would progress under doxycycline, but not methotrexate. So finally, taking it back to the 674 of us that were actually randomized, there's 47 more individuals of this response type than of this response type at 1 month. So this is something you can actually just go straight to the doctors who are actually implementing this clinical trial and say, this is what's happening to your individuals, your population in your clinical trial. So what's nice is you get to see a snapshot, almost like a time series across time. So that 0.07 increases to 0.12, so 15%, sorry, 12%, 15% at 3 months. And then it starts going back down again as people start dying in your clinical trial. So the set of always survivors actually starts to diminish. So again, at the 3 months, you're saying that regardless of treatment, you would estimate at least 101 individuals to survive regardless of treatment post-randomization at 3 months, but whose cancer would progress under methotrexate, but not doxycycline. So it's a nice summary of what's really happening in your clinical trial. Now, as I mentioned earlier, really as the clinical trial goes on, you get a very deep understanding of why people drop out and why people are dying, And also at 6 months, you can actually, I haven't shown this in the analysis, but you would actually see that at 6 months, more people, and you'd have statistical evidence for this, that more people live with the new treatment, doxycycline, but not methotrexate. So the estimates, once you make the monotonicity assumption on survival, they just go up. And so, earlier this was 0.07, so it's still the same, but these estimates have gone up, right? This was earlier, I think, 0.15, now it's almost a fifth of your population, right? And earlier we had no evidence at 6 months, for individuals, regardless of treatment, would still be alive, but whose cancer would progress under methotrexate, but not doxycycline. So we have that at 6 months now with with the monotonicity assumption. Now for this result to be wrong based upon, this monotonicity result, we would actually need all 12 individuals to have died, really, to have all died with the, doxycycline, but not methotrexate. And their cancer would have actually not have to have progressed with the methotrexate. But given what you've seen earlier in the clinical trial, this seems very unlikely. So the evidence here is still also very strong. Now, I do have a little bit of time, and you can further refine the sensitivity analysis if you should decide to do so. I think, the continuous results are also nice. The continuous treatment results. So, say if we were in this clinical trial, right? I won't get into the math here because it's quite intense, not intense, but it can be a little bit hard to read, and I'll get straight to how we would use this theorem. So this is our data. So one important consideration for us is, even if doxycycline extends our life, delays cancer progression, we still want to see that our quality of life really is better with doxycycline in comparison to methotrexate. So the analysis here is tricky. So what the study investigators did was they randomized actually a questionnaire. So I think, there was I think with probably a third, you would get this questionnaire on your quality of life. So I think 93 individuals got this questionnaire, and 107 on the methotrexate arm got this questionnaire. And then at 12 weeks, 30 had dropped out, I think, with the methotrexate arm, and 23 had dropped out in the doxycycline arm. So this is our data. So those of us that are alive and are observed and have a quality of life above 70 under the doxycycline arm are 73, under methotrexate is 89. Below 70, it's 136 for the doxycycline arm and 89 for the methotrexate arm. And then dead is just 13 at 12 weeks and 11 for the methotrexate arm. So it's just a simple contingency table. And then you can just very simply just calculate this risk difference with randomization and a suitable missing data and survival monotonicity assumption is a lower bound on this guy, right? It's a lower bound on the proportion of all of us, right, that would have survived regardless of treatment, would have not dropped out, and whose quality of life would have been better above 70 with metotaxone, but below 70 with docetaxel, right? So this is troubling if this were true, if this were positive, minus the proportion of individuals, regardless of treatment, would have not dropped out, would have still been in the trial, and their quality of life is above 70 with docetaxel, but below 70 with metotaxone. And we seem to have weak evidence for this, actually. So if you look at the data, you go back to that contingency table, this factual contrast, this risk difference, is roughly around 0.05. It's close, it's straddle zero, but it's nearly there, right? So what you're saying is that actually your quality, there's 5% more individuals in your population. So 34 out of this, 674 would have survived regardless of treatment, but their quality of life is above 70 with metotaxone, but below 70 with docetaxel. So that would be somewhat worrying for these 34 individuals, right? And there's 34 more individuals of this response type than where it goes in the opposite direction, right? But if it's a risk, if it's just a simple, if we're really saying a small difference, right? If it's all like, if all 34 would have a quality of life of 69 with docetaxel and then 70 with metotaxone, we might not really worry. So we want a clinically meaningful, difference. And so that's the next step we would do, right? We would just look at something as, so I won't get into the sensitivity analysis quite yet. You can do very suitable sensitivity analysis for this situation to relax the monotonicity assumption on survival and the missing data. So the way, okay, I'll get into it. Sorry, I do have time. So we calculated this risk difference earlier. So that was 0.05. We introduced two sensitivity analysis parameters. This four actually, sorry. This minus this, right? So you would have to work with the study investigators to think through what this risk difference would be. And so this entire contrast is equal to this thing, marginal across, whether or not you had dropped out. So we would conservatively speculate, this risk difference, which is this thing here, to be 0.06, because we had seen that this minus this is 0.05. So I would roughly think that the people who have dropped out conservatively should follow the same pattern. Like it shouldn't go in the opposite direction. The people who drop out, I think, are pretty close to the people who are still in the trial. And then the other sensitivity analysis parameter is just this guy here. And this thing here also makes sense, right? At 12 weeks, we've already established almost that, docetaxel increases life expectancy in comparison to metotaxone. So this should be negative as well. So as a sensitivity analysis with randomization alone, you have pretty solid evidence actually that, there's evidence for people who are going to survive regardless of treatment, but their quality of life is below 70 with docetaxel, but above 70 with metotaxone. So the next obvious question, as I alluded to earlier, is that, well, we really want a meaningful quality of life difference, right? If it's 70 versus 71, I really don't care. I might, that one, who knows whether it's really that meaningful. So then you do a very simple analysis, right? You just provide the same table. Instead of 70 is 75. And now you don't find evidence. So you redo the analysis with a similar factual condition. And you now don't find evidence that there's individuals in your population that would survive regardless of treatment at 12 weeks, would still be in the trial, but their quality of life is above 75 with metotaxone, the old treatment, but below 70 with docetaxel. So that's very nice at the population level that you don't have this clinically meaningful difference in quality of life at the individual level. So I think we're getting close to the end. So there's not much more actually for me to present. You can do the similar sensitivity analysis, and you can work with study investigators to really think about what is happening, in your clinical trial. And you can get really good ideas for what these sensitivity analysis parameters should be. And you would still think, going through the worst case, this would still be around 0. So you don't find evidence really that you have these individual level causal effects where the quality of life is better with metotaxone, the old treatment, but not the new treatment. So this brings us really quite to the end of my presentation. I thank you for your time, but I want to just very briefly, discuss the advantages of what I'm suggesting over previous approaches. So the first one really is that, for me at least, and I presented this earlier to the Food and Drug Administration, and previous methods really go way beyond randomization to talk about causal effects in the presence of truncation by death and informative censoring, and that's problematic, in some cases. So we are really the only ones to do this right now, so which is quite nice. But the other reason, so randomization gives us this very nice individual level interpretation, right? So, when you randomize, you want to talk about, all of us who are in the clinical trial, we want to know what is the best thing for us, for me, for Jaffer, or for you, what is the best treatment for you? Obviously, you can't know that, but the next best thing for you is really how many more people benefit with this new treatment in comparison to the old treatment. But if you're dead, if you're dead and you're looking at your quality of life with the new treatment, you really don't care about your quality of life with the old treatment. You're dead. So it really only makes sense for you to talk about, your quality of life, or, if we're talking about anything else, any other outcome other than survival, if regardless of treatment, you're still alive, right? So Don Rubin is quite right in this, that, it really makes sense for us to be very careful with what is the estimand we're talking about in these settings. But not only do you want to talk about it at the individual level, right? You will really want to say what is clinically meaningful, and that's what we're providing. The next thing, I'm almost done, is that, when you look at survival analysis, I have deep appreciation for, the giants in survival analysis, Tinshikai, LJ Wei, others at very, different institutions. But from a, clinical perspective, when we talk about hazard ratios, they're extremely hard to interpret. The worst case situation is when the Kaplan-Meier curves cross. Then we really don't have a way of, interpreting these results. What is that? What is a clinically meaningful hazard ratio? Becomes very tricky. It becomes very hard to communicate with people. From a regulatory perspective, I have to admit, I struggle very much when we go way beyond randomization. So the idea of like sequential randomization, what Jamie and others propose at Harvard, where you imagine a sequentially randomized clinical trial, is still a huge assumption in the randomized clinical trial setting. And we really don't know what happens if those assumptions don't hold. This is something that made me think quite a bit. If you randomize, you're getting a lot. So when we impose data burden, on the clinical trial people, that data actually is coming from us, say, in the clinical trial. How likely are we going to be willing to give, quality of life measurements or other measurements? They're not easy to collect. They're expensive. So from a data burden or a differential privacy perspective, we really want to impose, in a lot of settings, the minimal sort of data collection need. So this was quite nice. Transparency, everything is very transparent here. You get to see what is happening at the individual level. So how each individual unit in your clinical trial affects the population level results. And taking all of this together, I think you can work very effectively with collaborators to talk about what's happening in your clinical trial. So that brings me to the end. I thank my advisor, Tyler. This was a lot of fun to work on with him in the last 2 years of my dissertation. I got very valuable input, very excellent input and guidance from my committee members, Eric Chekin and Jamie Robbins. I had funding from NIH and SAMC, this last 3 years, just training grants. And then I'd like to thank Michael Hudgens for giving very useful advice on this work even in this year postdoc. And I thank Peng Ding and Limbo for sharing the data set. Thank you.
Thank you, it's very nice. So anyone have any questions to Jaffer? So let's first of all give Jaffer applause. Please, if you have any questions, yeah, go ahead, just feel free to ask. Chris, you are having any question? Oh, okay. So anyone have any question to Jaffer?
Oh, and please don't hesitate.
Yeah.
Don't feel embarrassed at all. If you have any question, it looks different, but I'm very, very happy to answer anything.
Jaffer, can you stop the sharing so that everybody can see you better and then have a discussion that way? Any questions for him?
Okay, I would just ask a very kind of general, like naive question. So in this kind of causal model, in fact, can you? I mean, have you actually considered about including any other variable except this kind of treatment X there?
Yeah.
So condition, other continuous or other variables.
Yeah, so that's actually a very good question. Let me just share the slides once more. So I actually got this from papers. Now, there's 2 ways about doing it. The way you could do it, say if you actually wanted to get close in a simple randomized setting, to know actually who benefits, right? Like who is actually at the individual level, like what are the covariates that would make someone always survive and then their cancer progresses? So like almost like precision medicine. You can do it. The way you would do it is you would include a set of covariates, even continuous, in this inequality. You would adapt this this expression. So you would have and C is equal to in C, right? So the set of all covariates you have and C is equal to C. And then here, you are actually getting the risk difference and C is equal to C. Like, you could actually tailor it down, you could whittle it down to exactly, hopefully, like, which are the set of individuals? Like, what are their covariates? Like, is it very healthy people? Is it, these genes? Any of that, you could incorporate in like this expression to get at what is you can look at heterogeneous treatment effects, etc. The other way to do it, the simpler way, is just to like subset on. So they're almost equivalent. You could just subset, doing a sort of like what is it called? I'm forgetting now. You subset on the covariates and then run each of the null hypotheses. So they're very similar approaches. The reason why I don't is like with 336 and 338, that's still a modest sample size. So getting at these more precision medicine type results, you really need the sample size. But I think if there is a very nice rich data set where you have that information, I think that would be a very good thing to do.
Right, thanks. So any other question? I think if you ask questions after you finish the question, if you can like mute yourself, it would be better. Otherwise, there was a kind of echo there, which we cannot hear very clearly. So any other question to Jaffer?
Yeah, Jaffer, I have a more of a philosophical question for you about clinical trials. right now there are so many drugs for or vaccines for COVID-19 which are in phase 3. And there is a rush now. Many countries are actually thinking about start vaccination program even before completion of phase 3 trials.
Yeah.
So there is that argument that don't do it or do it, because I think in many countries it's getting out of hand. Now I know the technical answer, which is that no, you should not do it until it's scientifically proven. But then, given what we have, what's your own philosophy on that? Start vaccinating program based on the success of the first 2 phases?
Yeah, it's a very good question. So I'll give as complete of an answer as I can.
I can barely hear you, Jaffer.
Sorry, can you hear me better now?
Yeah.
Okay. So one thing to realize is, you look at the history of clinical trials, and you look at exactly what you said. You look at clinical trials that have actually gone through phase 1 and phase 2, right? Phase 1, I almost discount, right? Because really, they're just too small for us to really get anything. Phase 2, you're talking about modest sample sizes. But those that have even passed phase 2 for, establishing like a dose, they're really done for toxicology. You might get a little bit of efficacy there, but not much. But if you look at historical results, you would be surprised, like so they passed phase 2, and then you're running a clinical trial on the new treatment versus placebo, or new treatment versus an old treatment. You want to take a guess of how many actually would pass at that stage? It's still half. It's crazy. Because you would think with the evidence at phase 2 that it should be above a half. But no, we really don't have, the phase 3 is I think in most settings, I would be very uncomfortable with with evidence based on phase 2 alone, given what we've seen in previous settings, that that half of the phase 3 results are ending up in failures. But then the other aspect of it is I think it's really unprecedented. When you're talking about very easy transmission, reproductive numbers that are very high in some settings, and then mortality that is higher than in other settings, obviously higher than in other settings. I would still I think what is happening here is the right thing. I think you really need to do those phase 3 trials, but then do it coordinated. What they're doing here is don't have every hospital administrator decide that they will run the same clinical trial. Instead of doing a meta-analysis, the same protocol. Really coordinate much better. So have it, streamline it very effectively. And then the other thing that they are doing, which I was a little bit scared about, was they were doing, and we've seen this only a few situations in history, is where they actually give the vaccine and then they give a little bit of a live dose of COVID, to the participant, potentially healthy people who would be less likely to die. So that to me, I understand the need for it. I think, jumping the gun in this situation can actually be quite dangerous. Just today, I think, right, we had situations, right, I think in Chad and Sudan, where they're giving the attenuated live polio vaccine, right? And that led for the first time in a very long time, an outbreak based upon a vaccine. So we want to be careful. Supposedly some vaccines actually increase your chance of getting infected, and maybe actually potentially make us more at risk of developing worse symptoms, more likely to actually die. I think, here, I really, follow under the camp of it's premature. It really is not the right thing to do, to just roll out, a vaccine before you have that evidence.
Thank you.
Okay, so do you have any other question for Jaffer?
I have a question.
Go ahead, Rika.
Jaffer, thank you for the very educational talk. I found it very interesting. My question is that first of all, I found that the idea of incorporating quality of life, the assessment with regard to quality of life, very interesting. But I have a question that um, I, of course, it wasn't talked about a lot in detail how it was really assessed. But isn't it a bit subjective because the perception of quality of life would differ from one person to another? So how was that taken into account?
Yeah, it's a good question. I think, I think the way we use quality of life, exactly what you're raising, this point that, quality of, let me share the slides once more to re-emphasize this point. Do I have that ability? No, I might just actually then just say it instead. Or actually, let me just share. So, with quality of life, the reason why I think sometimes we hesitate to use that analysis is precisely what you're saying is subjective. But, that subjectivity is still at the individual level, right? Like, between different people, like maybe I would think I'm more under, like if I'm under some pain, I would report, 75, but someone else would report 65, right? Or less, even 55, right? So it is subjective. But in a sense, that subjectivity is important, right? Because at the individual level, if I'm saying, oh, I'm really right, then the doctor is really considering my subjective response. He wants to take care of my subjective response. So I see your point, though. It is that, like, we're borrowing strength across individuals. So we're using randomization to borrow strength. So this, lower bound still is at the individual level. It's like you're at randomization, even that subjectivity is like incorporated at baseline. So like, the characteristics that perhaps would make me, say, oh, it's going to be 75, that pain level. There should be an equivalent sort of person with my sort of subjectivity in the control arm. So with randomization alone, it's like, that sort of difference, in subjectivity washes out too. So like the sort of like, oh, the healthier people, the people who complained more, all of that also balances out in both of the two arms of the randomization. So it's interesting. I think reason, you highlight a very good point. The other thing why we didn't use quality of life, like other people don't, is precisely this thing of it being on a continuous scale. Like, what is the clinically meaningful difference in order for, and as you're saying, like for the physician, right? Like when I see 70, above 70, below 70, we don't really have a understanding of what 70 is. Like, is above 70 really good? So 70 here is actually the median, like quality of life response. So, but a physician would know, right? Like on average, he would look at people who are reporting, 80, and he sees them and he sees that, oh, they're mostly pretty good. But then when he sees the 50s, they're really struggling to come into the hospital. So I think, you're completely right in the sense that, as a statistician, we won't have that understanding, right? But, once the subject matter expertise comes into it, you can incorporate that in your analysis. So I think, like when you look at clinical trials, they rarely ever give like the first is survival, the secondary is cancer progression. And then at the very end, maybe they'll report quality of life. But, you know, at the end of your life, like for me, if I was in this clinical trial, I might well want to sacrifice, you know, a month or 2 weeks if, if, if the other treatment is giving me a much better quality of life, you know, I'd want to spend that carefully with my family, right? So I think that analysis should be done. It just needs to be carefully done and carefully explained. Yeah. Thank you.
Thank you.
It's great. I think we still have a few more minutes, and if you have any question, please feel free to ask Jaffer. I actually, since if you are sharing this slide, I also have a question to you, Jaffer. So here, I think I remember you mentioned about what about sometimes people would like to look at what's the difference between 70 and 71. So what does that mean? So you use a different kind of comparison between using like a 75, found that it is kind of significant or not, compare the difference. So I just wonder whether there is any kind of like a possibility, try to, because you never really know what would be the other value you would like to use. So right now you use like 70 as the median time, median life.
Right.
But what about sometime like for another group or for another, you know, like a location or like a subgroup, they would like to use a different value. So, or another hospital for whatever reason. So is it possible to look at or to use this kind of comparison to build some kind of curve, or try to look at the change point regarding the significance level or somehow?
That's a very nice question, actually. This is a very interesting question. So I think one way of doing it, I think, so I'll first, the tangential question, right? Like, I think across hospitals, like across, you know, we have to be mindful a little bit about transportability, you know, like the results in one place, do they hold in another place? I think for the most part, you know, when we see, the phase 3 clinical trial comes out, it's like, we decide, no, it's gonna work everywhere, you know? Rarely do they implement it. You know, that's not completely true. Like, you know, you will have the clinical trial done here, and then you'll have the clinical trial, potentially the same clinical trial done in Japan or other places, just to establish, you know, the dosing and everything, and that it actually is the same phenomenon. Now, for your change point question, I think the direct one, I think the analysis would be deeper, but one thing you can do is like, you can think of, so I've framed everything in a frequentist setting, right? You can think about this from a fiducial or like a Bayesian perspective. And you can think about exactly what you're saying, you know, like you can say like, like you go back to this result, and you could like look at, so this thing is equal to, you know, the change point exactly. Like, when is it? So this is up to you. You decide this YA is a subset of R. This YB is also a subset of R, right? And so here I've said that they're the same, right? I've really said that, you know, 70 and 70, right? YA and YB are 70, greater than 70, greater than 70, right? But you can, exactly what you're saying is that you can work at like, at what, how big does the difference need to be, you know, in quality of life in order for this entire thing to go to zero, you know? So what is the evidence from the data in terms of change point? Like, you have evidence that there's some difference in quality of life. How big does that difference need to be in order for you to say that there's no individuals in your population with that much of a difference in quality of life? Does that make sense?
Yeah, great, thank you very much. Okay, so you guys, if you guys have any other question, actually you can still stay here to ask and discuss something interesting with Jaffer, and we can still stay here for another 15 minutes. And if not, you are free. And before we go, actually, let's thank Jaffer again. Thank you. It's very nice talk.
I'm very grateful for coming.
Yeah, thank you for giving us a talk. Even though sometimes there is kind of like, you know, difficulty Because this virtual talk, they always have some kind of, issues sometimes. So yeah. Yeah, you guys, you're free to stay here and share anything, or any research question or any other question with Jaffer. And if you